As soon as my system here starts recording, I think it's up now, and I'm going to hand off to Angel, and we'll let him take it from here. Looks like we got good participation today, Angel, so this will be great.
Okay. Okay, can you all see my screen now?
Yes.
Yeah.
Okay, so,
yeah.
Well, first of all, I would like to thank you all for being here today. We are going to share with you some information that we have from our test track. I would like to show you results, final results, but in fact, most things that we have are just questions. So the thing is that we have started recently to study the performance of two sections with Femin stabilized soil. We have to do we have to study them very carefully during the next month. So, okay. First of all, there is a Spanish catalog for payments, and that catalog has an analytical design behind. In the catalog, we also have a catalog for subgrades. So you can see here different type of subgrades. E1 corresponds to a low quality subgrade, medium low, I would say. E2 is a medium high quality subgrade. And then E3 is a very high quality subgrade. That's a real good subgrade. All of these subgrades have a Femin stabilized soil layer on the top. This could be like the capping layer of the subgrade. And almost always we use 30 centimeters, which is like 12 inches. So this is the study we are conducting is just to study this material. I should say that on the top of these subgrades, we always require a bearing plate modulus of 300 megapascal, which is a really high value compared to a conventional soil. So, this type of subgrade, you can see here the subgrade, which is this Femin stabilized layer on top of the soil. We typically use these subgrades in the highways, in the main highways. In fact, when you build a new highway, you are enforced to use this type of subgrade. And the typical situation is that we use this subgrade with a crushed granular material on the base of the pavement and then an asphalt layer. And this asphalt layer depends on the level of traffic, and we can go from 5 centimeters, which is 2 inches, to 35 centimeters, which is 14 inches. For the highest levels of traffic, we use a very thick pavement. This could be the situation of this layer in a typical pavement in Spain. So traffic is always a bit far from this layer. So as I said, we have a catalog, and sometimes we also do analytical design, and the catalog has an analytical design procedure behind. This is the typical idealization that we are typically doing in order to design these types of pavement. So what we typically do is that we join these two layers, the Femin stabilized layer and the soil layer, and we use a unique layer. So we model the subgrade like a half space, and we assign a 300 megapascal modulus. Okay, then we compute typical analytical design. We compute asphalt strain, vertical strain at the top of the subgrade, and then we apply a fatigue load. Okay, it is a matter of fact that this approach is quite unrealistic. We actually know that the performance of the subgrade is going to be very good, so we never worry about the performance of this type of subgrade. So, but there is a growing need to consider the performance of the cement-stabilized materials from a mechanistic empirical point of view. The first thing is that, what do we mean by cement-stabilized soil? Because I see that all the different countries have different names for similar material, or maybe the same name for different materials. So when we mean cement-stabilized soil, we mean that we use typically a medium-high quality soil, a soil that has, the soil can have some plasticity, like you can see here, the plastic index below 15. You can have some organic contents, sulfates, but it's not a very bad soil for sure. And then the level of cement, the amount of cement is typically over 3%. In fact, the normative requires that the minimum content of cement should be 3%. And then we mix it on place, okay? So this is a very big difference. So we apply a cement mortar injection, we mix it on place, and then we compact it. We also, just to have an idea of this much of the cement-stabilized soil, we require a compression strength of 1.5 megapascal after 7 days. And the modulus values that we are typically obtaining from back calculation are between 800 and 2000 megapascal. So it is a very high quality if we compare this material with a conventional soil, but it is not like a soil cement, for example. For a soil cement in Spain, you would use a very high quality soil, and then you would obtain modulus with a modulus which is around 10,000 megapascal. So, but for sure this is not a soil. This is something which goes further than a soil. So the objective of the research that we have started just recently, we have been collecting information for several years, but we are starting now to make a deep analysis of the data. So we want to validate a mechanistic empirical approach for designing pavement with cement-stabilized soil layer. So these are partial objectives, like we need to know the initial modulus of the material, we need to know the type of distress mechanism that we can expect from this material, which is not, at least it was not quite clear before this test, and we expect that we will be able to produce a model that will be able to reproduce the stiffness evolution of the cement-stabilized soils along the life of a flexible pavement. So we are hoping to be able to reproduce curing of the cement. We have found different literature, different publications where this topic is very nicely reproduced, and we also need to be able to reproduce the chain of the stiffness of these materials as a consequence of damage due to loading, mainly due to loading. And we also want to know the moisture effect on this type of materials. So we have to develop or to validate a damage model, because it is possible that we will find.
Welcome to GoToMeeting, online meetings made easy. There are 7 other callers on the call.
The determination of model parameters. First of all, we have to develop the models. We have to see which parameters are influencing are taken into account by the model, and then we have to manage to determine this parameter in the laboratory, so that we can apply the model to a specific cement-stabilized soil. Here you can see the sections that we have been testing, and sections 1, 4, 5, and 6 were fully flexible sections, but there were 2 sections, section 2 and section 3, that had this type of material. You can see here this this is the acronym in Spanish for the cement stabilized soil. So this material that you can see here on top of the subgrades of the sections 2 and 3, this material is cement stabilized soil. So section 2 has a thickness of 30 centimeters for this material. This is the typical thickness that we use in Spain. And section 3 has 25 centimeters, which is slightly below the first value. So we wanted to see the performance of these two sections, and we wanted to see the difference in performance between section 2 and section 3. I should say that these two sections were supposed to have 12 centimeters in the asphalt, but in practice this section, section 2, had also a thickest asphalt layer. Okay, so there are some differences between the stiffness of this combination of layers, asphalt and soil and cement stabilized soil, in this section and in this section. Well, this is the water table because we conducted the test with a water table that was close to the surface of the subgrade. From here to here we have 1 meter. So the first thing that we did some laboratory testing. First of all, we did the testing of the soil that we were using for the stabilization. You can see here the specification of the Spanish normative, and then you can see here the results that we obtained for a specific soil. So you can see here that we require the amount of filler to be below 35%, and here we have 20%, and we require the liquid limit to be below 40 and the plasticity index to be below 15, and well, this soil was not very bad, so this soil was able to fulfill this requirement. You can see here the requirement for the organic content and for the sulfates. So the first thing is selecting the soil, and then the next step is adding different quantities of cement and testing for strength, compressive strength. And the Spanish specification established 1.5 megapascal for the compressive strength. So in this case, just with 3% cement, which is the minimum content according to the Spanish normative, just with this 3% cement, we could have a compressive strength which was over 1.5 megapascal. So this was the compressive strength that we were obtaining after 7 days for this material. Okay, we also did some laboratory characterization in order to see the modulus of the material. Probably the most important picture is this one here, the modulus versus density. So we use we prepared this laboratory specimen by using a vibratory compactor, and then we determine the modulus in compression by applying a 10 Hz sinusoidal loading. And well, you can see here in blue the modulus evolution versus density. This is after 7 days, and then you can see here in red the evolution after 28 days. So at the beginning of the test we were expecting a modulus around 2000 megapascal. The requirement of the density, of the in situ density, is 95% of the optimum density. So this point, 95%, was the target in the field. So this is the most important thing. There was another thing that we studied, and we wanted to study the susceptibility to plastic deformation of this soil. So, because the feeling, the idea that we all had in mind was that plastic deformation could not take place in this type of material. So in order to do that, we prepared 4 specimens, and then we tested the specimen we tested them to permanent deformation. We applied sinusoidal loading, and we applied up to 900,000 cycles. And then we used 2 different levels, 0.42 megapascal, which is 60 psi, and 0.62 megapascal, which is 90 psi. The blue level, this blue level is the level that we would be expecting at the top of this layer, right below the asphalt layer. So what you can see here is permanent deformation divided by the applied load. Okay, so here in the blue line we have that divided the permanent deformation by 0.42, and here we have divided it by 0.62. So the thing is that this pattern was not expected, because we were expecting, and according to plasticity, you should be expecting a higher ratio when the load increases. Okay, so in practice, the typical result that we should be expecting would be that the red line is over the blue line, because this is epsilon permanent deformation divided by the level of the load. So these differences might be due to sample variability, or there might be something else. But the thing is that this type of performance is not the performance that you would obtain for a plastic material. So according to this, to the small differences between these 2 curves, we should not be expecting permanent deformation. Besides, we made a logarithmic extrapolation. Here you have the information concerning to the 0.42 megapascal, which could be the level that we have right below the asphalt layer at the top of the feminine-stabilized material. There was a very nice fit with a logarithmic model, and here we did a logarithmic extrapolation up to 1.7 million of cycles, because this is the maximum number of load that we have been applying in the test track. And even for this maximum number of cycles, the plastic strain is below 5,000 microstrain. So yes, this is a very rough number. If you multiply the plastic strain by 300 millimeters, which is the thickness of the layer, you would obtain only 1.5 millimeters. Of course, this is quite unrealistic, because this level, 60 psi, would only take place at the top of the layer. At the bottom of the layer, the vertical stress would be so much lower. So the thing is that the main conclusion is that we should not be expecting permanent deformation from this material. Now, in order to see the evolution of the stiffness of this material, we conducted FW testing periodically during the test. One of the concerns is related to conducting FWD back calculation in this type of sections. Well, in the first place, back calculation would be, from our point of view, would be unable to distinguish between this small layer. This is a soil, and this is another soil. This soil 1 is slightly better than soil 0, but in practice we didn't try to obtain this modulus, the modulus of soil 1 layer. We obtained a modulus for the combination of these 2 soils. So this was the first thing, which probably was not a very important simplification, but there were 2 additional problems. The first one is that here we have the asphalt layer, which is a stiff material, and here we have the cement stabilized layer. This comes from Spanish soil. This comes from estabilización, which is stabilization, and then 3. So this material is stiff. This material is also stiff. So it is quite difficult to distinguish this layer, the effect of this layer from this layer. And there is another concern which is related to bonding condition between this layer and this layer. The thing is that if you assume full bonding, then this structure will be very strong because these two stiff layers will be working together. If you assume that there is no bonding, then the structure will be very weak. But when you do back calculation, you have to assume a specific condition. So in the first place, we assumed full bonding. So this is the structure that we use in order to do back calculation. Now, here you can see the evolution of the stiffness of this soil cement stabilized soil. This is the material that we are dealing with. This is the modulus that we obtain. Here you can see in the x-axis you can see the number of loads, the number of passes of the vehicle. Each vehicle of the test track weighs 6.5 tons, so it is equivalent to a 13 tons axle. It is a very aggressive axle. So you can see that at the beginning of the test the modulus was around 1500 megapascal, and remember that we were expecting 2000 megapascal from the laboratory. I should say that these 3 points, when these 3 points were obtained, the time of the test was around, the age of the material was around 30 days. So this modulus should be very close to this modulus. And in fact, we believe it's very close, but we had the feeling that we were underestimating the modulus of this material at the beginning of the test. You can see here in blue the modulus that we obtained along a line that is out of the wheel path. Okay, these points here, the black points correspond to the center of the wheel path. So here we have damage. We have damage here, and here we do not have damage. Here we only have moisture effect and aging effect. So we also know that we had a compaction problem with this material because this line and this line were built in different moments, the very same day, but not at the same time. And the compaction level that we achieved for this line, for this path, the compaction level was not very good. So this is why we were obtaining a lower modulus. Okay? This 1000 megapascal modulus is very low for this material. But for sure you can see that there is an evolution along the test. You can see that the evolution seems to take place from the beginning to cycle 800,000, 1 million, okay? This is around 1 year, okay? So modulus evolution due to cement curing took place around during the first year, which is also according to different references. So when you see here the evolution due to damage, the first thing that we were surprised to see is such a fast damage. We saw that the material were decreasing the modulus very quickly under the loads. And in fact, when we were at this point of the test, around cycle 300,000, we were expecting this line to come to almost zero, or maybe to 100 megapascal. But the fact is that the modulus got stable around 500, 600 megapascal, which for us was a very high value. We were not expecting that type of performance. We were expecting this to come to maybe 100, 200 megapascal. But this was a bit surprising for us, this stabilization. So this is for section 2. Section 2 is stiffer than section 3. And here we have the result for section 3. Okay, for section 3, you can see here that the modulus at the beginning of the test is also around 1500 megapascal. You can see here the black points. These black points correspond to the loaded line of section 3. And again, you can see a clear decreasement of the modulus during the first half of the test. And in this case, the modulus got stable around 400 megapascal, which was also surprising for us because this is a relatively high value. I should say that we extracted also one core in cycle 1 million, and we extracted the core in the non-loaded line here out of the wheel path, and we saw that the modulus that we obtained in the laboratory for the core was very similar to the modulus that we were obtaining from back calculation. Now I'm going back to section 2, and in section 2 we have the same result. So the modulus that we obtained for the cores were very similar to the modulus that we were obtaining from back calculation. So these modulus represent the material with no damage, and these modulus represent the material with damage. So,
Angel, this is Buzz. Can I ask a question?
hi, sorry, I didn't hear you very well, Buzz.
Can I ask a question here? I hate to interrupt you, but
Sure.
did you say that you had density problems in both test sections, or just in section 2?
No, just in section 2.
Okay, so
But
what you've shown so far then kind of makes sense intuitively if you've got long-term curing going on outside the wheel path with no damage outside the wheel path with higher
Sure.
numbers in section 3, right?
Yeah, well, yeah, I mean, for section number 2 that you are watching right now, for section number 2 there was a compaction problem for this line. So that is the reason why this modulus is very high. So the realistic values would be for section number 3. Okay, for section number 3, the original modulus for the non-loaded line was similar to the loaded line, and this increased a lot. So in fact, when we took a core from section number 3, the modulus was around 3000 megapascal, okay? And when we took the core from section number 2, the modulus was around 16 megapascal. So we have the feeling that the results that we are obtaining from back calculation are realistic. That's the feeling that we have.
All right, thank you.
Okay, so here you can see the evolution of the material, the modulus of the material for the two sections. Okay, you can see here in black color the points corresponding to section number 2, and you can see here in red color the points corresponding to section number 3. So the first thing is that you can see that section number 3, we only have data for this section up to 1 million cycles, more or less. And the thing is that this section was completely destroyed up to this cycle. So when we came to this cycle, we have to reconstruct, we have to rebuild the asphalt layer of this section, of section number 3. But for section number 2, the performance was so much better. At this moment, we're still testing section number 2. So this point corresponds to auscultation, FWD auscultation that we conducted last December. So, well, when you see here section number 2 and section number 3, the first thought is that, okay, section number 2 is performing better because the thickness is also higher. Okay, so you can see here the thickness, total thickness of section number 2, and then total thickness of section number 3. So in some ways these differences make sense, but when we were predicting the life of these sections at the beginning of the test, we were applying this formulation. We have used this formulation, this formula in Spain for different... Excuse me, I cannot hear you very well. Can you... Fred, can you repeat your question?
It's not me asking the question. I don't know who asked the question.
Okay. Okay, I cannot hear you very well. Can you hear me?
Perhaps I should type it into the window.
Okay, but can you hear me well? Fred, can you hear me well?
I hear you very well.
Okay, okay, fine. So I will keep on.
I think there's some background noise on somebody's connection that's coming in.
Yeah, it sounds like there's a kid somewhere.
Okay. Shall I continue?
Yes.
Okay, I will continue. Okay, the thing is that according to this formulation, when we compute the stress at this point and the stress at this point, we were expecting a very large difference between this section and this section. In fact, as I wrote here, fatigue load indicates very large differences in N, I mean the useful life. So we were expecting very big differences between section 2 and 3, in particular by 2 orders of magnitude. So the first thing is that when you see this formula, and in this formula you can see that the exponent of the stiffness, the exponent of the stress is 15. Very small differences in stress means a very large difference in fatigue life. So this is the first thing. S would be the tensile strength of the material. So when you see this performance, it seems like modulus has decreased similarly in the 2 sections. The other thing is that at the beginning of the test, we were assuming this tensile strength, because this is the typical value that people think here in Spain, or we were all assuming for this material. This value represents the long-term strength of the material. But then if we introduce this value here in this formula, we would be obtaining a fatigue life which is so much larger than the fatigue life that we have seen in the test track. And on the contrary, if we use 0.32 megapascal, this is the value that we obtained for laboratory testing after 28 days. If we use this value, then N would be so much smaller than the fatigue life that we have seen in the sections. So this is one of the first questions that we have is that should we use this value? Should we use this other value? Maybe we should be changing S along the life of the payment. This is for sure one of the questions. The other question was this asymptotic performance. We were really surprised to see that the modulus were stable in relatively high values, especially for section 2, because 600 megapascal, that's a very huge value, even though the material is damaged. So if this is the real performance of the material, then it could be really great, because even after damage, the material would be able to retain a very high modulus. So this was the other question, is why are we getting this stabilization for such a large value of the modulus? No. Now, we also measure the performance in terms of different variables. We use FWE testing, as I have just presented, and we also use permanent deformation. We also measure longitudinal unevenness, cracking, and we also measure the performance from sensors. So, concerning the permanent deformation, here you see a graph for all of the sections, the 6 sections. So you can see here the permanent deformation in millimeters, 25 millimeters could be 1 inch, and you can see here the number of cycles. Okay, and here these points, these blue points here correspond to asphalt temperature. Okay, here in red you can see section number 2, and here in pink you can see section number 3. Okay, so the thing is that the section with the highest performance was section number 2. In fact, all of these sections have already failed, but one of the worst sections was section number 3. Remember that the main difference between this section and this section was only 2 inches of cement stabilized material. So this is the modulus. Okay, in this picture you can see the modulus of the soil. This modulus represents the modulus, the material that is below the cement stabilized soil, and you can see the modulus of a medium quality soil. We had around 100 megapascal at the beginning of the test under dry conditions, and then after water table level stabilization we had a modulus around 50 megapascal. So for sure this decreasement of the modulus also contributed to the damage of the cement stabilized soil. Now, what about cracking? Concerning cracking, we see something similar to what we have just seen for permanent deformation. The section with the best performance is again section number 2. Here you can see it in red, section number 2. And the section with the worst, of one of the worst performances, was section number 3, that you can see here in pink. So again, in cycle 400,000, I'm going back, you can see that in cycle 400,000 the permanent deformation was very low, and then permanent deformation started to grow. Now when you see cracking, you can see that at this point when permanent deformation was very low, cracking appeared, and then cracking started to grow also. So in fact the performance of the 2 sections were very different. Section 2 had such a better performance than section 3. And in fact this was expected according to the typical fatigue law that we use for semi-rigid materials. Now, as I said, in cycle 1 million that you can see here, we finished the test for this section. What, in fact, for cycle 1,050,000 cycles. So we had to repaint the section, so we took some slabs from the asphalt layer. And this is, for example, one of the slabs. This is a transverse slab. So we saw that there was bottom-up cracking. You can see here the crack, and in this case the crack was also visible on the surface. We have to say that we use this material here is a conventional asphalt concrete. In fact, this is a low quality asphalt concrete. For the wearing layer we were using an open graded mixture. This mixture that you can see here, this is an open graded mixture, and it was very difficult to see cracking through this wearing course. But for sure most of the cracks were bottom-up cracks. You can see here another crack here. Here you see another crack, bottom-up crack. Although the thing is that we really didn't know whether or not these cracks were bottom-up or reflective crack. For example, this one or this one. Is this crack bottom-up or is it reflective cracking? Here you can see again this type of bottom-up cracking, either bottom-up or reflective cracking. We were not expecting to see reflective cracking here because the modulus of the Femin stabilized soil was not very high, so we were not expecting reflective cracking. And we are not sure whether this is reflective or bottom-up. Here you can see one of the slabs. This is the transverse direction, and vehicles would be moving along this direction. And one interesting thing that you can see here is, okay, this is a transverse slab. In fact, you can see clearly the permanent deformation from the asphalt. You see the wearing course here is thicker than here. One interesting thing is that not in the center of the wheel path, but like 50 centimeters, 70 centimeters, or 60 centimeters from the center of the wheel path, we have this type of cracking. And probably you can see this better here. Again, this is like 50 centimeters far from the center of the wheel path, and there was a shear cracking. I mean, this type of shear could be caused by shear forces. So at some point, so the thing is that we thought at some point that there could have been a shear failure of the Femin stabilized soil, and that shear failure would have caused this. So this is one of the hypotheses, that there was a shear failure of the Femin stabilized soil. So one more thing that we did during when we did the forensic testing in section number 3 is that we conducted penetrometer testing. So here you can see the depth, okay, in centimeters. This could be the depth of the Femin stabilized soil, which is 25 centimeters. This 0 corresponds to the bottom of the asphalt layer, right the top of the Femin stabilized layer. So, and here you have depth, and in the x-axis you can see the penetration, which is in centimeters per drop. The interesting thing is that here in pink color you can see the confidence interval for the penetration along a line that was far from the center of the wheel path. So this interval of penetration is representative of the penetration in an area where there is no damage. So the thing is that we were expecting, okay, this pink, this is the interval for the material with no damage, and then each one of these lines correspond to different points along the center of the wheel path. So we were expecting this material to be highly damaged, so we were expecting this penetration level to be here. So we were expecting a higher level of penetration, but in fact we were surprised to see that the soil seemed to be in good condition. So we were certainly not expecting this result. And we also did the same thing, but in the transfer direction. Okay, so here these different lines correspond to different transverse positions. So for example, here line 10 is the center of the wheel path, and you can see that in the center of the wheel path, this dashed red line, the penetration is the same as in the non-loaded area, and the only point where we obtained higher penetration was here in line 17. This line is 17 centimeters, which is almost 1 yard far from the center of the wind path. So this high penetration value could indicate some damage, and at that point that could be an explanation for a shear failure. We also have a lot of information coming from sensors. We didn't have time to make the analysis of all of the information from all of the sensors, but here I'm just presenting the information from several soil pressure cells that were present at this level. So in order to make a comparison, I am including the information from section 1. This is soil, this is plain soil, from section 2 and from section 3. And this is like half a meter, like 50 centimeters below the top of the soil grade. So this is the reference section, this is section number 1, and you can see here that at the beginning of the test, these black points correspond to the beginning of the test. You have here the vertical stress, okay, and you have here the asphalt temperature. Of course, you see that the stress is increasing with asphalt temperature, and during the test, the stress level kept increasing. So this is at the beginning of the test. This was after 200,000 cycles. These blue points correspond to 500,000 cycles. Then these green points correspond to 1 million cycles. And these additional points correspond to cycle 1.3 million. So we draw this line, this green line, that we wanted to have as a reference in order to compare to the other sections. Remember that this line is representative of a fully flexible pavement with a high level of deterioration of the asphalt mixture. This increase in the stress level is mainly due to the deterioration of the asphalt mixture. So this is the information from section number 1, and of course for section number 2 the stress level was very low. Again, you can see here the stress level corresponding to the beginning of the test, and you can see here the evolution during the test. And you can see that the vertical stress is almost constant during the test. But for section number 3, the performance was very different. Again, you can see here the black points. These black points correspond to the beginning of the test, and you can see here the evolution during the test. In cycle 200,000, you have these points. For 500,000 cycles, we have the blue point, and after 1 million cycles, we could see this high level of damage. And this was even surprising for us, because the level of damage here, we knew that level of damage was very high because we saw the performance of the section. We knew the section were highly cracked, but we were surprised to see a level which was over the stress that we measured in a fully flexible pavement. And actually, after the reparation of the section, we repaved this section and we put a new material which was stiffer than the original asphalt layer. When we rebuilt section number 3 in cycle 1 million, so after this we rebuilt section number 3, we just removed the asphalt layer which was highly cracked, and then we put another asphalt material whose stiffness was relatively high. And now then we saw a very clear decrease of the stress level that you can see here with this family of points, red points or the orange points. So this is just another interesting thing that we did, is that I said at the beginning that in order to do the back calculation, we have to assume full bonding between the two layers. We were using EverCalc back calculation program. So in this program, you have to assume full bonding between the layers. But we we made a special back calculation program. In fact, the back calculation program was made some years ago here in CEDEX. The name is CIMA. And with CIMA back calculation program, you can introduce different hypotheses in your payment. So the thing is that we used that program, and we also introduced the asphalt strain in order to do the back calculation. So we did back calculation in order to fit deflection, and at the same time in order to fit asphalt strain under the pass of the vehicles. So when we do that, the good thing is that bonding between the two layers, asphalt layer and cement stabilized layer, that bonding strongly depends on the strain that we measure at the bottom of the asphalt layer. But probably I should say the opposite. The strain that we measure at the bottom of the asphalt layer is highly dependent on that bonding between the two layers. So we could back calculate bonding. And here you can see here in black color the original back calculation assuming full bonding. Then in red color you can see the back calculation assuming no bonding. So the red points would be assuming that there is full slippery between asphalt and cement treated layer. And then in yellow you can see the back calculation, the results of the back calculation introducing partial bonding. Basically we saw that at the beginning of the test, the modulus, the original back calculation was underestimating the modulus, but then as soon as the test started to develop, the situation was similar to the full bonding situation. So this was an interesting result that we obtained. So what we know for sure is that whether if you assume full slippery or if you assume full bonding, you are going to obtain completely different values for the cement treated layer. So that's the reason why we are not 100% sure that we are obtaining reliable results. And that's also one of the reasons why we are expecting to do the forensic analysis in a few months, hopefully next month or maybe in 2 months. And we expect those forensic analyses to help us understand what has happened to this section. So this is just a summary of the question that we have now on the table. We want to know for sure the types of distress mechanism that we have present, that they are present in the cement stabilized soil. We want to see whether or not there is lack of bonding, and we want to know whether there are bottom-up fatigue cracks, and we also want to know whether or not there was shear failure. For the asphalt cracking, we want to know for sure whether the cracks were fatigue cracking from the bottom of the asphalt layer or reflective cracking. So we are doing some trench so that we are expecting to see cracking in the cement stabilized soil and then cracking in the asphalt layer. So we are doing those trenches in order to see whether or not cracking was fatigue or reflective. Well, this is an important point. We would like to be able to consider shrinkage, the contraction due to the cement curing, and also low temperature contraction effects. So I don't know, maybe we will be able to find some kind of transverse cracking which is going throughout the complete through the complete pavement. Okay, we want to see if there is any clear crack which is going transversely across the whole pavement. Concerning the modeling, we want to validate a model in order to reproduce the modulus reduction due to loading. Okay, so first of all, we will select different models. We have seen some models that could be applicable, so we will select 2 or 3 models and we will try those models in order to reproduce the performance in the test track. We also want to know the parameters of the model, and the goal is being able to determine those parameters from laboratory testing. And of course, we want to see time effect. We want to see we want to validate a model which is able to reproduce the increasing stiffness due to cement curing. As I said, the most important thing that we have to do now is the forensic analysis, and we're expecting to do additional coring. We want to know the modulus of the material, and we also want to know the strength of this semi-stabilized material. We're also planning on doing FWD back calculation, but by applying the deflectometer load on the top of the cement-stabilized layer. We want to remove asphalt layer, then put the falling weight deflectometer on the cement-stabilized layer, and then apply the load. Because this way, we will get rid of one of the unknowns in the back calculation, which is the asphalt layer. So we are expecting to have reliable results by conducting this test. Then we want to see also cracking. We want to see whether or not there is cracking in the cement-treated layer. So we are expecting to do trenches. And we might be doing also penetrometer testing. So these are the questions that we have on the table, and as I said, we started to do the deep analysis of the data a few months ago, and we are hoping to have this finished by just a few months, maybe in 3-4 additional months, and for sure before this summer. So this is all my presentation. Thank you for your attention.
Can I just make a very quick comment, Fred, calling from South Africa. If you look at the paper that was presented at the CEDEX conference in 2008, you will see a lot of similarity with exactly the same type of failures and some answers to your questions in the paper on the tests in Mozambique. I'm not going to labor the point, but it was CTB and it also thin asphalt and on sand bases, but I would urge everybody just to look at that and see some very interesting similarities to the comments here.
Would you be expecting here to see a bottom-up cracking in the cement-treated layer?
The layer is too thin to have that, but what we saw is shear. We saw debonding. We could actually determine slippage between the asphalt and the cement-treated material, and we could see the fracturing of fatigue in the asphalt, in the cement-treated materials.
And did you see reflective cracking also?
We saw reflective cracking, and the cracking is certainly coming from a load reflection, coming from the deformation of the cement-treated material.
Okay, I will read carefully that paper.
Good.
Thank you.
Angel, this is Buzz. In the data in our current research cycle on our track, also in back calculation and analysis, we're seeing some significant things related to the quality of the bond between different layers in the structure. So, and we're doing a lot of investigative work to try to determine exactly what's happening, and is it happening as a function of tack material that we're using. My question for you is what type of tack material did you use when you built this, when you paved on top of the cement treated base?
Well, we use a small content of bitumen that has a very high penetration. It is a very soft bitumen, and we use like 1 pound per square inch. No, sorry, 1 pound per square yard. So, in fact, we did some testing in the laboratory just to make sure whether or not that bonding would be effective. And what we saw is that the bonding was really, really weak. It was not, in fact, a matter of strength, but a matter of stiffness of the bonding.
I think that's consistent with some of the things that we're seeing. The slip condition or the bond condition between layers is a function of quality of the tack and also the material that's used in the tack more than maybe we realized it was.
But do you have a report on the information that on the research that you have been conducted in NCAT?
No, that work is very much ongoing, and we have someone who it's part of their PhD program here in the research that they're doing with track data. So there's going to be a while before we get published information, but we've done a lot of back calculation analysis so far, and I'm convinced there's an effect there, and you know, defining it doing right now. So I don't think we've got anything published on it yet.
Okay, I will be looking forward to see those results. Thank you.
Can I just interject very quickly? Also, the horizontal slippage is actually such that you can see the slip on the surface, and you can actually see how the material in the wheel path and outside of the wheel path are moving longitudinally. So this slip is real, and you can see what is known in the English language as slicken side, or a very slippery surface where it breaks the bond.
But how can you mean that you can see the slippery on the surface?
Yes, see the slippage of the whole asphalt layer on top of the cement-treated layer.
When you have kind of a complete debonding, I mean a complete lack of bond, you certainly can see that, because we've seen that type of thing here on pavements I think as thick as 10 inches on crushed granite bases. You know, when we've had a complete loss of bond, you can actually see kind of a change in the aggregate particles in the mix on the surface.
Well, we do not have that here for sure. I mean, from the surface you cannot see any movement of the particle in the longitudinal direction. I am almost positive of that. But maybe, I mean, I don't know. Maybe if we have the bonding, it is not enough to mean a movement of the asphalt layer, at least here.
I think, Fred, you can also see, I mean, you don't always have to see it. You know, when you have the quality of the bond changing and the amount of bond as it's going down in the inner layer, I think as a condition of the quality of the tack and the material used in the tack, you can see a back calculated debonding, quote, debonding effect when you don't have like full mobilization of material. You know, it's almost like just a lack of bond that affects your back calculation process, but there's not a full mobilization going on that would.
But what?
Something interesting that comes in, if as soon as you lose bond, there's a change in the whole stress distribution in the layer of the cement-treated material, and you'll see that the shear comes up, and it manifests so that, in fact, because of the debonding, you see exactly the loss in what you described earlier on as a structural competency. So you see exactly that going into the system, and that helps you to, you can actually measure that stiffness loss with a P-spar, for example, and you can see all of that happening. So without belaboring the point, I would urge just to look at that and get back to us if you have further questions. But I think we've got beautiful correlation between what we're hearing in the three parties here.
And I agree with what you're saying, Fred. My comments really are, if you have the same interface and you have one that's tacked with a relatively stiff material and one that's tacked with a relatively soft material, then the condition of the bond will drift more to full bond and more to no bond as you go from stiff material to soft material, and that's an effect that I think can be independent of this full debonding that leads to like a complete change in the stress distribution. You know what I mean?
I understand. I think the only one thing that I can comment we found is if you can change the surface texture so that the bond is also enhanced by a horizontal shear resistance, that also helps to do exactly what you're saying.
Yes.
But I mean, do you mean that because what we have seen in the test track is that when at the beginning of the test, when the stiffness of the cement-treated layer is very high, there seems to be a bit of debonding. But then, as that stiffness goes down, then the bonding seems to disappear and the situation is closer to full bonding. Is that compatible with what you said?
Angel, can you go to slide 3?
Number 3?
Yes.
Okay.
While you do that, Angel, what we've seen in some of our data is like if you pull samples, forensic samples, and you do bond strength testing on them at these different points in time to validate what you think you're seeing, we've seen cases where we get really high bond strength, but significant differences in fracture energy that make up the bond strength. So depending on how you interpret the data, you can see things in the bond strength data, in the shear strength data that can help you to explain what you're seeing in your measurements.
Okay.
Let's go to slide 7, Angel, because I think it's where you show all the sections.
Here?
Yes, here. Well, let me give you my take on this, Angel. Is we did a similar kind of experiment about 15 years ago in Louisiana, and what we found that is happening in this pavement is essentially you have a crumbling, so crushing of the material in the very top half an inch of the soil cement underneath the asphalt. Can you hear me?
Yeah, I can hear you.
Yeah. So in reality is because of the problems with curing of the soil cement, the very top half inch is very dry and is going to crumble very, very fast. Okay. So when you're going to do the trenching, you may be able to see this. The reason I think you have the same type of failure is the fact that when you look at the photographs of the asphalt slabs, you have fines going into the asphalt.
Sure, we have fines.
So to me it looks like you have exact same thing. You have a crumbling of the soil cement at the very top. And because of that, that translates also into loss of bonding, because it's like you would have the asphalt on a very thin layer of sand, and underneath the sand you have the soil cement.
And according to your experience, which is the typical depth, the maximum depth of that crumbled material?
It's going to be less than 2 centimeters.
Less than 2 centimeters.
Yes.
Okay.
If you go deeper, the material would be sound, would be very strong. But at the very surface, you have this layer of very crumbled material, which you lose the bond with the asphalt layer. In your case, I think because you have such thick asphalt layers, you have close to 5 inches, you have not seen the slippage cracking that Fred has mentioned. But we saw the slippage cracking in exactly the same way, because our asphalt layers were thinner, and the loss of bond underneath makes the asphalt to slide like a carpet.
Okay, but that's probably the reason, because we actually didn't see movement in this material.
Yes, because your layer is thick.
Yes. Yeah, we don't even have that movement in section, for example, 4, 5, and 6, yes, where we actually have a regular soil as a capping layer. So in section 4, 5, and 6, we don't see movement.
And a lot of work on this type of failure has been done by Maurice de Beer in South Africa, where essentially he looked at the crumbling of, resistance to compression of the soil cement, not fatigue. So you may not see any major fatigue cracking in the soil cement just because you have this failure and the layers are acting independently.
Exactly. In other words, what you're saying is that the structural system is failing, but you see a different performance phenomenon.
And there have been some efforts in the United States to look at the mechanistic empirical characterization of soil cement, and I'm not sure that this has arrived anywhere. As far as I know, in South Africa, they included in their mechanistic empirical design this crumbling failure. So there are some equations that look at the compressive strength and compressive behavior of the soil cement. And I know recently some work has been done in Australia, but it's probably going to be published and shown at the conference in Davis.
Australia has delivered a manual, a nice report on the performance of lightly theming layers. I didn't have the time to read it, but it seems to be a very interesting one.
In the US, we typically don't go with such a low cement percent. We typically go somewhere around 8 to 10% cement. But we still have the same problem because of the drying at the very surface of the soil cement. What is critical is after you place the soil cement, how do you seal the surface and how fast do you come with the asphalt on top?
Well,
what we found in Mozambique, talking to Stefan now, also going higher strengths, we found that the performance is different because you might have a very hard surface and less crumbling, and for that matter we prefer that. But then you must be very careful because if the layer is very small particles, then you can have slippage because of the hard surface, and losing the bond in a different manner. But other than that, I'm going to have to just go offline now and say thank you very much.
Okay, you're welcome. Fine. Thank you, Fred.
Angel, what type of curing did you say y'all used for the soil cement prior to paving on top of it?
What type of curing you mean during construction?
Yes.
Yes.
Yeah, I mean, when you build this material, the first thing you have to put a tack coat, which is just to prevent water from going away.
Right.
Because, I mean, just because you typically build this in the summer, so you don't want the material to go dry very fast. Right. So just after the construction, you have to put this protection, which is a bitumen material, and then just before you are going to place the asphalt layer, you have to brush that material, remove that material by brushing, and then put a different tack coat, which is the bonding tack coat, and then put the asphalt layer.
Well, one of the things I'd be interested in doing, and it's one of the things I hope we're going to do here, is to change the model and put an inner layer, add a layer to the back calculation that is in the interface, like a really thin layer in the interface, and then vary the strength of that with a full bond condition on both of the upper and the lower interface for it, and see if you can use the inner layer to capture the difference that you're seeing in your data. And Stefan, I think if you did that, then possibly you could capture the crumbling effect that you said y'all observed in Louisiana.
Well, we kind of saw the crumbling effect in the forensic analysis, and then we said, well, let's assume there is a layer that is very weak between the asphalt and the soil cement. And we did back calculation, we did forward calculation, and we found out that you lose significantly in the fatigue life of the section once you lose the bond.
Yes.
Yeah.
But can I, just one comment is that when we do back calculation, I think it's really difficult to back calculate the modulus of a very thin layer. You know what I mean? That
yes.
I wouldn't trust very much those results. And one of the problems that we have here with bonding and modulus is that we did some kind of forward calculation, and we saw that you can have two very similar deflection bows, almost the same deflection bow, by either decreasing the modulus of the cement-treated layer or keeping the modulus but decreasing the bond. In fact, we use BISAR, BISAR multi-layer linear elastic program.
Yes.
With that program, you can introduce partial bonding.
Right.
And the thing is that our conclusion was that it is not possible to distinguish from FWE back calculation. I mean, you would obtain, I mean, you cannot distinguish whether there is a low decreasing modulus of the cement treated or a loss of bonding. You know what I mean?
Yes, yes.
That's why we did this second back calculation. I will go very fast to the other picture. That's why we did the second back calculation. And in order to do the second back calculation, we introduced it. I mean, we did the back calculation from deflections. Okay, here it is. We did the back. Okay, in this back calculation, we have used full bonding. In the red back calculation, we have used full slippery. In order to do this back calculation, the yellow dots, we were using also instrumentation from the sections, because actually, if you have loss of the modulus of the cement-treated layer, or you have the bonding, that would make a very big difference in the asphalt strain at the bottom of the asphalt layer. So we use that data from the sensors in order to do the back calculation. And the yellow point is what we obtained. And we believe that at the beginning the bonding was lower because this modulus was very high, the modulus of the material, and then at the middle of the test the bonding was better because the modulus of the cement-treated layer was much smaller.
Right. Are you going to, in your forensics, are you going to be able to do some shear strength testing of the inner layer? Are you able to do that, recover samples so that you can do some shear strength testing?
I don't think we can do that because we have tried to take cores from the sections, and I don't know why. When we try to drill the core, we almost always we have the surface broken. You know what I mean? That the asphalt material goes in one piece and the soil cement in another
because
piece.
of the bond.
Probably because the bonding is not nice. Probably.
It would be really nice if you could somehow recover samples and then look at the fracture energy of the bond, because I think there's a lot of good information in that. This is great data that you have, Angel. We appreciate you making this presentation. This is awesome.
Yes, it's wonderful.
I hope for sure it has been very useful for me and for all of us, for Javier and Belén are also, they work here in the test track with me, and they are also, and Jose Orenfio is also here. The information that you are giving us is very useful for us. So we will be for sure looking at those papers you have been talking about, and I'm pretty sure I will come back to you again with additional questions, if you don't mind, sure.
Held in a week or so, I'm going to send you some papers or links to some papers, and not necessarily that we wrote, but you know, I looked at this topic with bonding for years, so
I really appreciate that, Stefan. I really appreciate that. May I ask you just a final question, which can be very useful for us now? Do you know which people in the United States are working better now with modeling of fracture of this type of material, fracture modeling of this type of material?
I
really don't know many people are working.
Stefan, I don't know of anyone who's doing a lot of work with that. Do you?
No.
I was thinking of published papers on this.
Okay. The University of Florida is doing a lot of work with fracture energy of asphalt materials, but with the cement stabilized base, I don't know of anyone who is.
Okay.
We're getting honestly in the United States, Stefan. I mean, I'd like to get your input on it, but we're kind of moving away generally from cement or for some cement treated bases because of the cracking problems that we've had.
The cement-treated bases were used extensively in Louisiana. In some of the states that don't have good aggregates. But I think the experience they have, and especially the fact that they have a very wet climate, kind of push them toward the increasing of the thickness of the asphalt layers and the reduction in the use of soil cement. But in general, they use a much higher cement content, 8%, 10%.
I agree.
That's a very high content.
It is. And many of the soils that they use for soil improvement is better to use lime than cement.
Well, I can imagine, because in fact, we did testing of one section with lime stabilized soil, and the performance was really, really good.
Yeah, I'm talking about the Louisiana soil. They have clays. They don't have the sand that you have experimented here.
Oh, okay, okay.
So they have fat clays, you know, PI of 45, you know.
We're not using it for stabilization. We're using it for modification most of the time when we use it.
When you mean modification, you mean like a soil cement?
Well, not to make it like a low strength concrete, but to make it more to reduce the plasticity index of the.
Okay, okay, I understand.
Angel, if you can send me email me a copy of your presentation, then I'll make it available with the other files that we have.
I will do it right now.
That'd be great, and we appreciate you guys taking the time to do this. And for the benefit of everyone who's still on the line, the next presentation is on March the 8th. That'll be done by Kansas State University on their APT program.
Fine.
All right, we appreciate it very much. That was very interesting, and I'm gonna stop the recording. I did record this, Angel, so as long as everything made it okay, then we'll make that available also.
Okay, that will be fine.
Thank you very much, Angel. Thank you.
Thanks to all of you for being here.
Bye.
Bye.